Dynamics. So last year in statics, you learned how bodies at rest react to forces, or how to analyze forces in bodies at rest. And now, in dynamics, we move on to how bodies respond to forces and motion. All right? Dynamics can be split into two branches. These are kinematics. Kinematics is the geometry of motion and the relationships that we use to describe motion. For example, velocity, position, velocity, accelerations, relationships among them. So these are all of the tools that we use to describe motion. The second branch is kinetics. Kinetics is the study of the relationship between forces and motion. The most common relationship that you're probably familiar with is Newton's second law that says the force equals the mass times acceleration. So here the force is related to the acceleration, a quantity of motion, by this equation. So throughout this course we will study both kinematics and kinetics in succession 3 different times. First we will do kinematics and kinetics of particles, then we'll do kinetics and kinematics of systems of particles, groups of particles, and then we'll move on to kinematics and kinetics of rigid bodies. So let's start with the most basic form of kinetics, which is called rectilinear motion. Rectilinear motion is a relatively complicated way of simply saying motion in a straight line. Now the first thing we have to do in order to describe the motion of a particle in a straight line, or in any situation, the first thing we have to do is define a coordinate system. This is a reference system that we use to describe the motion. So, for example, if we have a particle moving in a line, imagine a car going down a road, a train going down the train tracks, something like that, a ball rolling across, a pool ball rolling across a pool table. These are all examples of things that could be moving in straight lines. So for the coordinate system, we pick an origin there and we indicate a positive direction. So I'll pick the origin to be here and I'm going to call that O for origin. And positive is to the right. So a coordinate system, you always pick the origin, the point of it, and then you pick the direction that is positive. In this case we only have one direction. When we move to 3-dimensional motion you may have 3 directions to pick positive. We'll get to that later. So here we have a coordinate system, we have an origin, and suppose we have a particle moving along that line. Here's our particle. Again, maybe it's a car going down the road or something like that. And we can call the position of that particle P. So P is the position of the particle, O is the origin of our coordinate system, and then we usually choose a coordinate. In this case we'll call X. So X is the measurement of the point P from the origin. O is the origin itself and P is the point itself. Now let me pause just for a moment and point out to you, in a small aside, the importance of vocabulary. So I've already started throwing out a lot of the vocabulary that may be new to you, for example, rectilinear motion, coordinate system, and more importantly, the one I mentioned is particle. Throughout the semester you'll pick up a lot of new jargon, new vocabulary system that we use in dynamics and mechanics in general, and it's really important that you understand the specific meaning of these words in the context of mechanics. So keep up with the vocabulary as we move through the semester. In this case, a particle for us, a particle is an object whose orientation is of no concern. So we're not worried about the orientation of the particle. Imagine a ball, a tennis ball, and you throw it up in the air. that tennis ball, although it will spin, and you can analyze the spin and the motion of spin, in general you can consider the motion of that tennis ball independent of its orientation. So you throw it up in the air, it comes down, maybe it hits the ground and bounces or whatever. Its orientation and all that is unimportant. It doesn't matter to how the ball moves very much. Okay? So we call that a particle, we reduce it to a specific point, and we analyze it that way. Later, when we get to rigid bodies, we'll start discussing objects whose orientation matter to us. Suppose you have a knife and you're playing a game of mumbly peg and you throw the knife in the air and it twists and spins and it falls to the ground by your foot. You're going to be very interested in the orientation of that blade when it hits the ground or hits your foot. Is it coming into your foot blade first or hilt first? Now the orientation matters quite a bit. So that's just an example of the difference between a particle and a rigid body. For now we're going to be working on particles. Okay, so back to our coordinate system. So we have our origin, our coordinate system, we indicate positive, we measure the position of the particle with x. Let me continue this coordinate system and maybe add some measurement indicators. Perhaps these tick marks indicate some measure of interest or a dimension such as meters or feet or inches, dimensions of length. Okay? So in this case, the position of P, or the position of the particle at point P, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So x equals 11. And then we have some dimensions of length. So the braces mean dimension L, dimension of length. For example, this may be meters or feet or inches or rods, chains, cubits. These later dimensions we won't use very often. We will see meters, feet, inches, perhaps millimeters, miles, things like that, kilometers quite a bit. Okay, so that's the coordinate system. If our object happens to be in the direction opposite that which we indicated as positive, so the left of the origin, suppose I have a second particle, I'll put it here and call it P2 for the position of particle 2. Its coordinate I will subscript with a 2 so that we know we're talking about the position of particle 2 at P2, and its position x2 in this case is equal to 1, 2, 3, 4, 5 units of our dimension in the negative direction, so it's minus 5, whatever dimensions of length are appropriate. Okay. Now, when the position of a particle is known, for all time, for all possible values of time, so now x is a function of time. When you know that position, we say that the motion is known. We say that the particle motion is known. What that means or implies is that given the position of the particle for all time, x as a function of time, from that we can determine the particle's velocity and acceleration. And that's what we mean when we say the position is known. It means that we know the position, velocity, and acceleration of the particle for all values of time. So saying that the position of a particle is known means that it's given to us in some form. So it can be given as, for example, a function. For example, x of t equals 5t squared plus 2. There's a function. I can put in any value of time into this function and it'll tell me its position. Or x of t equals 3 cosine 2t. I put in the time. This equation tells me the position. I could be given the information for the position graphically. Here's time, here's the position x, and here's the graph showing me what that position might be. or another form is that it may be tabulated. Okay, typically we'll be dealing with functional representations of position. Right. Okay, so the motion is known. We're given the position for all values of time. It means the motion is known. All right. So let's consider the case where we're given the motion and we know the function describing this motion. All right, given as some function, okay? And we know, if this is our coordinate, here's O, and we know that at some time t, here it's time t, P is the position of the particle and it has a coordinate x. So position P is x at time t. Now suppose that some time later, particle is, let me subscript the P as a P1. So initially it's at P1. Sometime later it's at position P2. So later at P2, remember that's a subscript 1, the position is, let's say it's x plus some delta x, right? So if this distance is x, that interval is delta x, and let's say the time is t plus delta t. All right, so at some initial time it's at position x at time t. A little bit time later it's at a position x plus delta x at time t plus delta t. All right. We can find, with this information, the average velocity over that time interval. So this is equal to, the average velocity is equal to delta x over delta t. So over the time interval delta t, the particle moves by an amount delta x. And so delta x divided by delta t is the average velocity over that time interval. And this will have units of length per time. Okay. We can also find the instantaneous velocity. All right, so this previous average velocity, this time interval may be quite long. It may be, hours or something like that. Now the instantaneous velocity we can find as that time interval delta t becomes very small. And so we say that this instantaneous velocity is equal to the limit as delta t approaches 0 of delta x over delta t. Right? And this is the instantaneous velocity. I will call it v. We will generally use v as velocity. Okay? So this might look familiar to you from calculus, right? And in fact it is the definition of a derivative. So we can say that the instantaneous velocity is equal to the derivative dx with respect to time dt. And again, this has units of length per time. So meters per second, feet per second, miles per hour, kilometers per second, whatever. Okay. So given, again, if we're given the position as a function of time, we know that the velocity will be equal, instantaneous velocity will be equal to the derivative of that function with respect to time. And since we know the function, we can find the derivative, presumably. All right. Okay, so we can get velocity. We can also find, in a similar manner, the acceleration. The average acceleration is equal to the change in velocity over the change in time. So that is the velocity, go back to the previous page, so the velocity at time t minus the velocity at time 2 divided by the time interval. And the instantaneous acceleration, which we will use the lowercase a, is equal to the limit as time becomes very small, time interval, delta t becomes small, of delta v over delta t. And again, you'll probably recognize this from calculus as the definition of the derivative, so the acceleration is the derivative of velocity dv dt. That's the instantaneous acceleration. And this will have units of length over time squared. Now, it's important to point out that the acceleration, again, is equal to dv dt, all right? But this is equal to the derivative d dt. The velocity is dx dt, all right? So the acceleration is equal to the second derivative of x with respect to time squared. So, given a functional description of the position of a particle x, we can find its instantaneous acceleration at any time. Frequently, however, the information we obtain about the motion of a particle is not in terms of the position, but rather in terms of acceleration. So let's talk about determining the motion of a particle in this. A good example of this is Newton's second law, F equals ma. If I show you a body, I tell you what the forces are acting on it, and I tell you what its mass is, you can quickly find the acceleration. Now you have the acceleration. Can you tell me the velocity and position of the particle for all time? The answer is yes, you can, with a couple of caveats. Usually, information given to you about acceleration is in one of three forms. Either the acceleration is given to you as a function of time, or perhaps the acceleration is given to you in terms of a function of position. So a particle's position is known, and the acceleration, the particle's position is not known. Particle's acceleration is given in terms of position, or the acceleration sometimes also is given to you in terms of velocity. The second two cases we won't cover here. It typically requires numerical integration in order to solve them. So we won't deal with now. The first one, where the acceleration is given as a function of time, is relatively straightforward to solve. Now you may recall from the last lecture that the acceleration of a particle is equal to the derivative with respect to time. I can rearrange this algebraically and say that dv is equal to a dt. Now, knowing, as I mentioned before, the acceleration is a function of time, we'll call f of t. Maybe it's 5 cosine omega t. Maybe it's 6t squared minus 7, whatever. Some function of time is given to you that describes the acceleration. So now I can write this equation as dv equals the function f of t dt. I can solve this by integrating both sides of the equation. So I have on the left the integral of dv equals the integral f of t dt. Now, if I can do this integral, then what I get is the velocity is going to be equal to some function of time, right? The result of this integral will be some other function of time, and the result of this one will be the velocity. However, currently the form of this is an indefinite integral, which you may remember from calculus will yield constants of integration. Another way of saying it is that I need more information in order to do this integral. Okay, and the way this is represented here is by what we call initial conditions. So first let me say, so in order to do this integral, let me write it out, integral dv equals the integral f of t dt. So let's look at the right hand side. In order to do this integral, I need to know the initial time and the final time, then I can do the integral. So let's just say that the initial time is 0. We start at time 0, and we want the result to be arbitrary. So we want the result to give us a function of time, so to be good for any time. So we'll leave the final time arbitrary as t. Okay? So instead of saying from 0 seconds to 7 seconds, we're going from 0 to some arbitrary time t. In order to do the integral on the left-hand side, I need to know the velocity initially, that is the velocity at time 0. I also need to know the velocity at arbitrary time t. So the velocity at time 0 is what we call an initial condition. Initial by meaning at time 0. So we say that the velocity at time 0 is equal to v naught. That's our initial condition. Okay? So we can put that here, v naught, maybe it's 5 meters per second, maybe something like that, right? So that's a specific number we know. But remember, at the end of this integral, we want an arbitrary time t, so we're going to leave this as the arbitrary velocity v of t. Okay? So now I can do the integral. It's a definite integral given the initial conditions. Okay? And I can perform that integration. So if I do that, performing the integration results, the left-hand side is going to be v of t, the final, minus v naught. And the result of doing the integral is just the integral 0 of t, f of t, dt. I can't reduce that any further until I'm given a specific form of that function, f of t. So I can rearrange this a little bit and say that the velocity of t is equal to v naught plus the integral 0 to t, f of t, dt. So now I have an equation that tells me the velocity for any value of time. Okay? But in order to find that, I need to know the initial velocity, right? And I need to be given the form of the acceleration f of t and be able to integrate it. Right? Let's give this a name for shorthand. Just call it g of t. Okay? So I don't have to write all of that out. I'm just going to call that g of t. And the reason I'm doing that is so that now we can find the position for all time in a similar manner. Okay, and you may recall that the velocity is equal to the derivative of x with respect to time. So we're going to go through the same process we did previously, right? So that says that dx is equal to v dt. And now I'm going to integrate both sides of the equation like this. I'm going to get my initial condition. I'll use IC to abbreviate that. X at time 0 is x naught. Maybe it starts at 1 meter or something like that in our coordinate system. All right? So I go from 0 to t, I go from x naught to x of t in my integral. And so if I perform that integral, I get x minus x naught equals the integral. Remember that the velocity is a function of time. Up here, v of t is equal to all that integral, right? We're going to give it a shorthand notation, just call it g of t. So now my integral is g of t dt, and that goes from 0 to t. Right? Or rearranging that, I can say that the position as a function of time is equal to the initial position x naught plus the integral from 0 to t of g of t dt. And that is the description for the position as a function of time. And just as a reminder, g of t is equal to v naught plus the integral 0 to t f of t dt. which also equals the velocity. So, given information about the acceleration of a particle, in terms of a function f of t, I can figure out the velocity at any time and the position at any time, also given the initial condition. So the initial conditions are that x at time 0 is x naught, and v at time 0 is v naught. That's the end of lecture 2. In our last lecture, we saw that given information about the acceleration of a particle, we could find its velocity and position for all time. Let's now look at a couple of special cases of that. The first is called uniform rectilinear motion. So again, rectilinear motion is motion in a straight line. Uniform rectilinear motion refers to the specific case where the acceleration is equal to 0. Or a is equal to 0. Well, you'll remember where we finished up last time that given information about acceleration, we can find the velocity. And what we found is that the velocity as a function of time is equal to the initial velocity plus the integral over the time interval of the acceleration as a function of time dt. Well, in this case, the acceleration is equal to 0, so the entire integral is equal to 0, and we're left with the conclusion that the velocity is equal to v naught for all time. So in other words, the velocity for all time is going to be equal to a constant. And that constant will be the velocity it was initially when it started. So the velocity won't change. That makes sense. If the acceleration is 0, the velocity won't change. Okay? And now from the velocity, we know we can find the position. Again, from the last lecture, the position as a function of time is equal to the initial position x naught plus the integral of the velocity as a function of time dt. Right? Well, in this case, now we know that the velocity as a function of time is a constant, and the constant being the initial velocity, v naught. Right? So we can rewrite this integral, x of t now is equal to the initial position plus the integral 0 to t of v naught dt. And since v naught is a constant, it can be pulled outside the integral, so this is x naught plus v naught, the integral from 0 to t of dt. And the result of this integral is that the position as a function of time is equal to x naught plus v naught t. So we have that relationship and that relationship given the fact that the acceleration is equal to 0. And that's all you need to know about uniform rectilinear motion. Remember, that's some of the vocabulary that we talk about. Uniform rectilinear motion is when the acceleration is 0. The velocity will be a constant, and the position can be found from this equation. The second special case is called uniformly accelerated motion, or uniformly accelerated rectilinear motion, if you want to be long-winded about it. This is the case when the acceleration is known to be a constant other than 0 for all time. All right, so the acceleration as a function of time is just equal to a constant. All right. Now again, going back to our relationships between acceleration, velocity, and position, we know that the velocity as a function of time is equal to the initial velocity plus the integral of the acceleration dt. Now, we know that the acceleration is a constant, so that can be pulled outside of the integral, so this becomes v naught plus a naught, I'm sorry, just a, we're not using the subscript naught, a times the integral dt from 0 to t. So the velocity as a function of time is equal to v naught plus the acceleration times time. Let me add to this just to be clear, it's a constant. Okay, and now moving on to find the velocity, or excuse me, the position. Remember that the position as a function of time is equal to the initial position plus the integral of the velocity over the time interval, right? This equals x naught plus the integral from 0 to t. The velocity we just found, right? It's v naught plus a t dt. All right, and you probably recall how to do the integral. It's a simple linear equation that you can integrate, and the result is that the position as a function of time is equal to the initial position x naught plus v naught t plus 1/2 times the acceleration t squared. And to go with that, we have, just as a reminder, v equals v naught plus a t, and a equals a constant. And those are the relationships for uniformly accelerated motion. Remember, the important thing here is that we know that the acceleration is a constant. There's one more, so you have these three relationships. And there's one more that may be useful at times. Now the acceleration is equal to dv dt, right? I can use the chain rule to write this a little bit differently. dv dx dx dt. So I really haven't changed anything. I've just multiplied this by dx over dx, which is 1. I haven't changed anything. But I can rearrange this, right? And I see that dx dt, that's equal to the velocity, so that becomes dv dx times v, right? Okay, so I can rearrange this equation now. Let me go back and remind you, it equals the acceleration. So I can rearrange this and say that v dv is equal to a dx. And now I can integrate both sides of the equation, right? And just like we did before, using information about our initial conditions, the initial position is x naught, the initial velocity is v naught. Now time does not appear explicitly in this equation, so this integral goes, for dx it goes from the initial to some arbitrary final, x of t, and this goes from the initial velocities to some arbitrary final velocity v of t. Okay, and so if I do this integration, the result is v squared equals v naught plus 2 times the acceleration x minus x naught. So this can be a useful relationship. Again, this is only valid for uniformly accelerated motion, which means that the acceleration is a constant. Sometimes we're interested in describing the motion of more than one particle at the same time, even in the case of, still in the case of rectilinear motion. Let's begin with the example of relative motion. Suppose we have two particles moving along the same line. So if this is my coordinate system, x, positive to the right, here's my origin O, and I have a particle A here and a particle B here. Okay, this might be, for example, two cars going down a road, or two balls rolling in straight lines, something like that. Well, let's, from our origin, let's look at the position of things. First of all, this is the position of x. We'll use x sub A to denote that position. And then we have the position of B as well, which obviously we will call x sub B. So now if these two positions, as we have here, are measured from the same position, we can say that the position of B relative to A is written as follows. That is x, and we will use B slash A. So you read this, the position of B relative to A in the x-coordinate system. That's equal to the position of B minus the position of A. So that's a simple definition of the equation for relative position. And we can indicate that here on the diagram like that, the position of B relative to A. Now, I can take the derivative of this equation with respect to time, which leads me to conclude that the velocity of B relative to A is equal to the velocity of B minus the velocity of A. So the derivative of that one is velocity of B relative to A, derivative of xB is VB, derivative of XA is VA. And similarly, I can get the equation, the acceleration. Acceleration of B relative to A is equal to the acceleration of B minus the acceleration of A. So that's the relationships we use, and this is sort of your definition equation, if you will, of relative position. Okay, and from that you can infer velocity and acceleration. All right. Next, we're going to discuss dependent motion. This is the case where more than one particle has motion that depends on that of another. And here's a simple example in this picture. Here what I've drawn are two blocks, blocks A and B, and they're connected to hanging from a ceiling through a pulley system. So this symbol indicates, in this case, a ceiling. In general, that kind of a symbol means something that doesn't move, a wall, the ground, the ceiling, something like that. Here I have one pulley that's attached to the ceiling and another pulley that's attached to block B. And then there's a rope at one end attached to the ceiling. It goes around the first pulley, around the second pulley, and then attaches to block A. Okay? And I think you can imagine if you grab A and pull on it, block B is going to move. And the motion of those two particles are dependent on each other. Okay? In fact, there's a very specific relationship between their motion. And so how do we come about, how do we get that? Well, first we recognized that we have an ideal rope. By ideal means it doesn't stretch. So that implies that it has a constant length. So let me label, first of all, the positions of our particles involved. So in this case, we're going to say that our origin is the ceiling, and positive will be downward. Okay, and so I can say that the position of block A looks like that, x sub A, right? And the position of block B, as you're down from the ceiling, looks like that, x sub B. So these are the two positions of our two particles that we're interested in, and we want to come up with a relationship between them. Okay, let me label the segments of this rope that's involved. So here's A, right here to the contact point at the pulley. Since B is already used, I'll call this C. Around to this contact point is D. Down to this contact point E, and here F, and all the way at the top I'll call that G. So these are the points along this rope. Now remember, the rope is a constant length, right? So I can write an equation that says a constant, that's the length of the rope, is equal to each of these segments of the rope. So let me start here. I go from A to C is one segment of the rope, so I'll just call it AC, that's this length. C around to D is the next segment, D down to E, E around to F, and then F up to G. Right, so the constant, which is the length of the rope, is equal to the sum of each of these segment lengths. Okay? Now I want to point out something. First of all, this segment from C around to D, as I move these blocks up and down and so forth, I think you'll recognize that that distance is always a constant. It doesn't change, right? And the same with the distance around this pulley. That distance E to F doesn't change. So I can say here C to D is equal to a constant and E to F is equal to a constant. Right? And so what I'm going to do is I'm going to subtract those from this side of the equation, lump them in with this constant. Okay? We don't know what these distances are. We don't need to know them. That's the point, as you'll see in a moment. And so I can rewrite this as a constant equals the distance AC plus the distance DE plus the distance FG. Okay? This constant is a new one and incorporates these two, as I already pointed out. All right, next what I want to do, looking at distance AC, right? So I'm going to rewrite this equation again. So constant is equal to, all right, the distance from A to C, I would like to point out, it's related to the distance XA. And it's equal to this distance XA minus this distance here, from here to there, is equal to XA. But note that this distance is a constant, right? It's the same as the distance of this fixed arm that's holding the pulley up. So in other words, the distance from A to C is equal to X sub A minus a constant. I may not know what that constant is, but stay with me. As you'll notice in a moment, it doesn't matter. Next, the distance D to E right here. So you can ignore what's going on the left side. As B moves up and down, that distance from D to E changes and related to XB, right? In fact, it's equal to XB minus a little constant here and a little constant there, here and here, right? So D to E, that distance, is XB minus some constant, right? And finally, the distance from F to G, here to here, again, you'll recognize it's equal to X sub B minus that constant. All right. Now these three constants still, I don't know them, but I'm going to lump them all into the right-hand side. Right? And so I have the relationship that some constant, a new constant now, is equal to XA plus 2XB. And this is what's called my constraint equation. Right? The motion of particles A and B are constrained to move according to that equation, right? And now the most valuable part is that I can take the derivative of this equation. The derivative of a constant is 0, and the derivative of XA is VA plus 2VB. And likewise, the derivative again, acceleration of A plus 2 times the acceleration of B. So these are three constraint equations on the motion of the two particles. Okay? So if I tell you what the position of A is, I take A and I slide it down, and I tell you what that distance is, you can figure out what the, let me put it again, if I say I move it with a particular velocity of A, you can figure out the velocity of B. It's going to be minus 2 times the velocity, or minus a half the velocity of A. Okay, similarly the accelerations. So this is a case, and in this case, because if I tell you the motion of one particle, you can determine the other one. We say that we have one DOF. DOF for degree of freedom. Okay, although there are two particles, there's only one degree of freedom. All right. Let's look at one more case of dependent motion. It's similar to the last one, but now we have three particles, A, B, and C, again suspended from a ceiling with pulleys, 1, 2, 3, 4 pulleys, and a rope snaking over the pulleys. Okay, let's define our coordinate system first. Positive downward from the ceiling. There's the position of particle A, block A. Here's the position of particle B, or block B, and here's the position of block C. So now let's go through the same exercise before. We'll do it a little bit more quickly this time, recognizing, again, the length of the rope is a constant, right? So I can say that a constant is equal to, well, so here's how I go about figuring out these constraint equations. Go from one end of the rope and work your way to the other end. And as we go through each segment of the rope, note how it relates to the coordinates in your system. So, for example, if we start here, this first segment, I will note, is always related to XA. In fact, it's going to be equal to XA minus some constant, right? So let's just say, so this segment is XA, and the constant gets lumped into this left-hand side. This is a constant lumped into the left-hand side. This distance, right, as I move A up and down, this distance is always going to be related to XA. If I look over and move B up and down, for example, this distance isn't going to change no matter what B does. So this segment is related to XA and some constant. So I'll just write XA, all the constants go in here, right? So I've taken care of this segment, the constant, this segment. Here's another constant that gets lumped into, and now let's look at this segment. So this one, I think you can see, changes as X sub B changes. As block B goes up and down, this gets longer and shorter, plus these little constants. So now I have XB. That's this segment. I can check that. All right. I've done this one. I've done this one. Constant, constant. I did that one. Now I have to do this segment. Again, that goes with XB moving up, down. If XC moves up and down, right, this one doesn't change length necessarily. Okay. So that is plus XB, and all the constants go here. We've done that one, and now this one is related to XC. So my constraint equation is that a constant is equal to 2XA plus 2XB plus XC. And if I take the derivatives, 0 is 2 times the velocity of A plus 2 times the velocity of B plus the velocity of C. And for acceleration, so there are my constraint equations. Now in this case, notice that from the equation, if I tell you the velocity of one of the members, one of the particles, then you can't solve for the velocities of the other, right? You need to know two velocities in order to figure out a third. So in this case, we have 2 degrees of freedom.